Hello guys, this is Jin Chen and Yicheng Tao introducing to you our exploration of the interdisciplinary field of election theory, which combines the game theory knowledge of applied math and mechanism design section of economics research or public sector. Our group found an interesting phenomenon involving history, especially over these 2 decades, that sometimes a politician not the most popular comes to be the winner. Apolitically, we may want to put aside whether such outcomes are good for a country under national leaders elected somehow this way, yet we are sure that given that such elections are more or less electing politicians that fail to represent the most popular view and opinion among the public, it will often arouse different kinds of problems. So what kind of election algorithm would make a better and fairer result come into being is what we would like to discuss through this video, with the help of our reference paper completed by Harvard professor, Nobel Prize winner Eric Maskin, along with another expert, Partha Dasgupta. From the paper, what we should first set up is our 5 basic principles that guarantee and measure the quality of voting algorithms. These are Pareto or consensus, anonymity, also called one person one vote or equal treatment, neutrality, IIA, which is the abbreviation for independence of irrelevant alternatives, and above all, decisiveness. The property of Pareto suggests that if all voters prefer candidate X to candidate Y, then Y should not be chosen over X at any time. The property of anonymity requires that no voter should have more influence on the outcome of an election than any other, so that all votes should be counted equally. If voters are switched, the result must still be the same. For example, candidate X getting a vote from voter A, while Y getting one from voter B should be equivalent to X getting one from B, with Y getting one from A. The property of neutrality regulates that no candidate should get any kind of special treatment. The property of IIA dictates that if candidate X is chosen as winner against others from the feasible set, and now whether or not some other candidate Y will be removed from the set does not affect the result of X still being chosen as the winner. And last but not least, the property of decisiveness points out that a voting rule has to pick out a unique winner. It can be neither zero nor multiple.
So from the paper, we could get 3 prominent voting rules: simple majority rule, or majority rule in short, rank order voting rule, also called the border count rule, and plurality rule, also called first past the post rule. The rule for simple majority algorithm is that candidate X is chosen if for all other feasible candidates Y, more voters prefer X to Y than Y to X. While under rank order rule, each candidate gets 1 point for every voter who ranks her first, 2 points for every voter who ranks her second, and so forth, with candidate X being chosen if X point total is lowest among those in the feasible set. And according to plurality rule, candidate X is chosen if more voters rank X first than they do to any other feasible candidate. Note that what only counts here is how much for the first place of each candidate, which is just what real election utilizes now. In this way, it will be easy to find out that rank order voting rule and plurality rule fail to satisfy our IIA principle, as shown by the counterexample on page 951 of the paper. The candidate with the most votes wins, even if they did not receive a majority of the votes. And we can show that the majority rule violates the decisiveness principle by Python program as well. We assign 15 people to rank for 3 candidates, A, B, and C.
When we run this program, we could often encounter situations generating a so-called Condorcet cycle, violating the decisiveness principle, which is also called the axiom of decisiveness. So, you may want to ask, is there really some other voting rules that might satisfy all 5 axioms? Unfortunately, the answer is negative, given by one of those economists decades ago, whose name is Kenneth Arrow. In his 1951 book, Social Choice and Individual Values, Arrow proposed his Arrow's impossibility theorem, which states that there's no voting rule that could satisfy all 5 principles when there are 3 or more candidates, and Maskin points it out in our reference paper too. But it is too early to give up. we can still find something important from this seemingly pessimistic conclusion. In order to satisfy an axiom, a voting rule must conform to that axiom regardless of what voters' preferences turn out to be. In practice, however, even Maskin himself once addressed that Arrow's theorem describes. What Arrow's theorem describes are those looking for methods that work for any likelihood of ranking. Yet some are unlikely to come true. One reason for this may be ideology. You may never rank a candidate with an ideology too far from you to be higher than those sharing similar ones with you, thus generating a preference result in the graphic pattern of single peakness. Another reason may be polarization. You may never rank some candidates in the second place who are deeply loved by some people but hated by others. Maskin once mentioned an example that in terms of Trump's ranking, Republicans either loved Trump or hated him, causing rankings either putting him at the top or at the last position. Such polarized pattern also simplifies our once existing complication, making the actual cases getting easier. We could then show by our second Python program that does the simulation of assigning 1,000 people to rank for 4 candidates A, B, C, and D, whose levels of political ideology are 1, 2, 3, and 4 respectively, in an ordinal way, which then verifies lemma 3. We make sure these 1,000 people all have single peak preferences. That is, if one ranks B ideology number 2 as the highest, then there's no way D ideology number 4 would be ranked any higher than A or C, since ideology number 2 being the highest makes that person prefer 2 over 1 or 3 over 4 with the help of coding design knowledge. And we then use the results from running the program to verify the decisiveness of majority rule under situations of single peakness. Decisiveness of majority rule under situations of single peakness has thus been proved. We're still curious about how it works under situations of polarization, and we could show it by our third Python program that does the simulation of assigning 1,000 people to rank for another 4 candidates. We make sure these 1,000 people all rank A, either at the highest position or the very lowest, with the help of our coding design knowledge, and use the results from running the program to verify the more usual decisiveness of majority rule under situations of polarization. Note that the decisiveness of polarized voting ranks does not come by all the time. There are still times that indecisiveness exists, and these are just Condorcet cycle notations, and you may find it bothering.
So how to fix the indecisiveness of majority rule under situations of polarization? We develop a new strategy combining majority rule and rank order voting rule. If it first decides the winner using majority rule, if majority rule fails, that is, no one obtains a majority against all opponents, then among those candidates who defeat the most opponents in head-to-head comparisons, it selects as winner the one with the highest rank order score. To simulate improved majority rule, we write 2 more general methods, peak.vote and poll.vote, to provide the voting results under situations of single peakness and polarization, which take the number of voters and candidates as parameters. In this way, we can simulate improved majority rule with more voters and more candidates. We also write majority.py, which contains 2 methods simulating majority rule and improved majority rule. And we also write check rules.py to check the decisiveness and IIA of different rules under situations of single peakness and polarization. This is our peak.py and poll.py program. This is our majority.py program. This is our check rules.py program. Let's run the client code test.py, which employs all these methods to test the decisiveness and IIA of improved majority rule as well as majority rule. In this program, we give 20 random voting result samples under both situations of single peakness and polarization. We have 5,000 voters, 6 candidates, and the poll is candidate 2. The poll which is the candidate who can only be ranked first or last. We then use check rules.check method to test the decisiveness and IIA of both rules. And here are the results. As we can see, under situations of single pickedness, both majority and improved majority rule fulfill IIA and decisiveness, which is a result we have mentioned. However, under situations of polarization, chances are that majority rule violates decisiveness. In this case, our improved majority rule fixes this problem and provides a unique winner. For example, in this voting result sample, majority rule didn't give any winners, but our improved majority rule gives winner candidate 4. However, improved majority rule still violates IA because the winner before deleting candidate 1 is candidate 4, but winner after deleting candidate 1 is candidate 6. So further refinement is needed to fix this problem. Another interesting finding in this program is that under situations of single pickedness, winners are always candidate 3 or 4. We regard this as a good example of the median voter theorem, which implies candidates at intermediate position always win, since candidates 3 and 4 are middle candidates of 6 total candidates. In conclusion, improved majority rule guarantees decisiveness and IIA under situations of single pickedness. It also guarantees decisiveness under situations of polarization, so it is more robust than original majority rule. However, it still fails IIA under situations of polarization. Further refinement is needed.
So I hope you guys like this video and learn something from it. And thank you guys. Goodbye.
Goodbye.